guys. As you can see, we're back in the classroom. I was able to get permission to come up here and do this. A lot of you expressed that you liked having the lectures be as close to what they used to be. So welcome back from spring break. I hope you had at least something fun to do over the time. At least you didn't have any homework to work on. As you can see, we are starting chapter 8 now. This will probably be our last chapter together for pre-calculus. It'll probably take us pretty close to the end of the year, and we'll talk about maybe small things we'll do at the very end of the year. You can see the title of the chapter is Sequences, Series, and Probability. It is about 6 sections long. We'll actually split it up into 2 pieces. Sequences and series will be 1 unit, and we will take a big quiz on that, and then we will separately do probability, which will be separately tested on, quizzed on at the end of the chapter. Okay, so section 8.1, starting off with the title of sequences and series. So I think we'll probably just handle sequences for today, and then next lesson we'll go over what series are. So what is a sequence? A sequence is, in just real simple terms, it's an ordered list of numbers. Okay, and it's kind of key that it's ordered, meaning that there's a reason why you write the first number in its position and the second number and third number, and there's an order established. Notice that between the terms it's just a comma, so it's a list of numbers, and that's going to be the big difference between sequences and series, is what goes in between the numbers. So each number is considered a term of the sequence, and you could say that each term holds a relative position to each other. So, in other words, this would be the first term, second term, third term, fourth term, fifth term. I know that seems obvious, but we're going to need to work on the notation for that, and that's going to be key to what we're studying. Okay? So this book, not every book, is going to use a small case A for to stand for term. Now, typically we use T, but T looks too much like a addition sign, so that's why we're steering away from that as the variable. So small case A will be what we use to represent a term, and then we'll use a little subscript to denote what position it is. For example, in this one, if I wanted to tell you what the first term was, I would say A sub 1, but we'd never say it like that. We'd call that first term, and we'd say the first term is 2. We could also say something like the fourth term is 8. Okay, and you could pick out any position. This example over here, you could say, all right, the third term is 9, and the fifth term is 81. Now, if you took a quick look at those, you could see that, again, a list being ordered means there might be some sort of pattern to the numbers, and that's going to be key to what we're doing. So, we'll move on here. And this is where things kind of get a little more formal. We often describe a sequence by a rule. Okay? You might call it a formula, and it's in this book called a general or an explicit rule. Explicit meaning you can get any term you want from this formula. You don't have to know the first term in order to get the 50th term. That's kind of the power of an explicit or a general rule. For the nth term, and again, if we're trying to find the nth term, we would use n as the subscript to denote that we're looking for the nth term. In order to do this, we kind of go in forward and then reverse. Forward is, okay, give us the rule and make sure you know how to produce the terms of a sequence. And after you get pretty good at that, we put the car in reverse and we start talking about how do we find the general or the explicit rule if we only know the terms of the sequence. So this should be pretty easy, but I don't want to gloss over too quickly because you have to know how to do this in order to do the other direction. So if somebody gives you that the nth term of this sequence is given by 3 times n plus 7, if you wanted to find the first term, you would just plug in a 1. Okay, so the first term is 3 times 1 plus 7. So the first term would be 10. Most of the time you can do this in your head. If you want to do a little algebra off to the side, you can. Second term, so a sub 2, or the second term would be 3 times 2. or 6 plus 7. Third term would be 3 times 3, or 9 plus 7. And usually somewhere, maybe in the second, third term of producing the sequence, you can start to see the pattern. And that's kind of key, because seeing the pattern is going to help you when we go the other direction with it. You can see here that clearly these terms are going up by 3 each time, and that's probably because we're taking numbers 1 bigger each time and multiplying by 3. So at some point, feel free to maybe just produce the next term on your own without having to plug it in. Like, I know for a fact the next term is going to be 19. I certainly could verify that by saying 3 times 4 plus 7, so 12 plus 7. It says right the first 4 terms, that's just kind of random. It could be the first 5, first 6, whatever. Obviously, if you wanted to, you could keep going with this and find as many terms as you needed. Another example here, just showing you a couple of different patterns so that you maybe can help recognize them later. When you have -1 being raised to alternating powers between even and odd, that's going to make your sequence bounce back and forth between positive and negative. And that could be helpful later when we're trying to figure out how to represent the nth term of a sequence. So if we plug in a 1, okay, the denominator is going to be 5 times 1 plus 3, so that's obviously 8. But when you're in -1 to the first power, that's negative, so first term is -1/8. The second term, obviously going to be -1 to the second power. Even power of -1 is going to be positive. And you're going to have 5 times 2 plus 3, so 10 plus 3 is 13. 1 over 13. It's right about now that I could start saying each term alternating is just going to be positive and negative. So I don't really have to focus too much on raising -1 to the third power in this case. I know the next term is going to be negative. It's just now a matter of putting in 3 here, so 15 plus 3, 18. And even at that, as complicated as this one is, you could probably predict the next term of the sequence without even plugging in. You can see that the denominator is getting bigger by 5 each time. Okay, 5 times n, kind of like the 3 times n here. So you know the next one's going to be positive because you're raising it to the 4th power. You could probably say without too much work that the next term is 1 over 23. A couple things to notice there. These went up by 3's because of 3n. These denominators went up by 5 because of the 5n. Again, look for those sort of patterns when we start to go the other direction here in a second. Last one here, this one's got a base being raised to a progressively higher power, so that means this sequence is going to grow pretty quickly. 2 times 3 to the 1 minus 1 power, well, that would be 3 to the 0 power, so that's just 1. So the first term here is 2. Then if we plug in a 2 for the second term, it'd be 3 to the first power, so 2 times 3 is 6. Next term would be, let's see, 3 to the third minus 1, so 3 squared, 9 times 2, 18. And again, it's right about here that you could probably say, hey, I know I can predict what the next term is going to be, because all we're doing is just multiplying by 3 to 1 bigger power, so we're just multiplying by another power of 3. And as you can see, it's going 2 times 3, 3 times, or 6 times 3, 18 times 3. I can tell you without a doubt that the next term is going to be 54, because that's what 18 times 3 is. Okay? So again, look for what kind of patterns are being produced here by these kind of general or explicit rules, and then when we start going from given the sequence and we have to work backwards to try to find the nth term, maybe you can find a pattern to recognize. So this is where you kind of make or break yourself in this first section. It's one thing to be able to produce the terms of a sequence. That's basically that's a little bit of just arithmetic or plugging in and evaluating. The key is how you do it when they give you the sequence and they want you to come up with the nth term rule, that explicit rule. Well, this is one of the frustrating parts as a teacher, and maybe for you as well. It can be a lot of fun trying to figure out the patterns and figure out the puzzle, but I'm not going to be able to tell you how to do every single one of these problems. There's going to be some figuring out of a puzzle, okay? And you're going to have to try to play with things and try to adjust it and see if this works, and if it doesn't work, try this instead. And I know that can be frustrating for some, it's gonna be fun for others, because you get one of these aha moments when you do get the answer. You're like, oh, that's it, I got it, and I got it by myself. I didn't have a teacher tell me exactly how to do it. So the first thing I would encourage you to do is try to find the pattern. Okay, look at the sequence from one number to the next, what's happening. Can you figure out that they're always adding by a certain number, multiplying by a certain number, subtracting a certain number? Just look for any sort of pattern you can see. And a lot of times that pattern's easy to find if you look at the differences, like what is the difference between the first and the second term, the second and the third term, and so on. If that doesn't result in anything, maybe go down another level and look at the differences of the differences. Okay? And I'll show you what I mean through a few examples. And again, this is only going to show you 4 problems that have a little bit of variety to them. There's going to be all kinds of problems where you're just going to have to try to figure out the pattern on your own. So again, taking my advice on this first one, you can see that there is a pattern here that every term is just 3 bigger than the one in front of it. Okay, and if you remember over here, the first example we did when we were expanding the terms of the sequence out, we knew that there had to be a 3n involved. So I would suggest on this one that there has to be a 3n involved somehow, because you're getting bigger by 1 more multiple of 3 each time. Now you can see that if I plug in a 1, this isn't going to work, because the first term would be 3, and it's actually 4. If I plug in a 2, the second term would be 6, and it's actually 7. But right now you're starting to think a third term, 3 times 3 is 9. You can see that each term is actually 1 bigger than 3 times n. So maybe this would be the nth term rule, because 3 times 1 is 3 plus 1 is 4. Okay, 3 times 2 is 6 plus 1 is 7. 3 times 3 plus 1 is 10. And I think we can pretty much say from this point forward that that is going to give us any term of the sequence. Okay. So when you see a constant set of differences between terms, use that as a multiplying factor on your variable n, and it should get you close. Now I just call that the adjustment factor. Clearly this wasn't just 3, 6, 9, 12, but it was 1 bigger than each of those, so that's kind of the adjustment factor to make it work. On this one, it's going down by 2 each time. So you might say, let's put a negative 2n somehow. And that will help us go down by 2 each time we make n 1 bigger, but as you can see, negative 2 times 1 is not that. So what I tend to do on these ones that have a common difference, I say, all right, well, what would I need to do to get this first term? Negative 2 times 1 is negative 2. That's actually 4, which is 6 bigger, so let's try putting in a plus 6 and see if it works. We know it works for the first term, so negative 2 times 1 is negative 2 plus 6. If I plug in a negative 2, or I'm sorry, 2, negative 2 times 2, negative 4 plus 6, plug in a 3 to find the third term, negative 6 plus 6, looks like we've got it nailed. So again, you can see using that difference as a multiplying factor in front of the variable, and then just trying to figure out what the adjustment factor is. Now this next one doesn't look like there's a common difference here. It kind of looks like it, let's see, it went up by 3, then it went up by 6, then it went up by 12, then it went up by 24. So clearly there's no set pattern on the differences. You can certainly see a pattern. I think most of us could probably look at this problem and see that it looks like it's getting bigger by a factor of 2. Not adding 2, but you're actually multiplying by 2 each time. I think everybody can see that. So instead of putting 2 as a coefficient in front of n, let's use 2 as a base to a power. You might recall the third one we did over there kind of had that multiplying factor as a base. So when you see something kind of growing faster, more by multiplication than by addition, maybe use that multiplying factor as the base of an exponential. Now again, 2 to the nth power is, the first power is certainly not 3, and 2 to the second power is certainly not 6, and so on. So we have to make an adjustment here. We can see it started at 3, and then we just started multiplying by 2 from there on, but we didn't multiply by 2 to get to the first term, so you might want to say that, so that we get 2 to the 0 power to start with, and it looks like we want to start with 3, so how about we say 3 times 2 to the n minus 1. And again, this can start off as a 1 to get us 3 times 1, and then if we start putting in a 2 for the second term, it'd be 3 times 2, third term would be 3 times 2 squared, perfect, and so on. So I know this is quick, but you're just trying to look for any sort of pattern and then trying to kind of puzzle figure out what the nth term rule is. So again, when it goes up by a certain amount each time or down by a certain amount each time, difference-wise, you use that as a coefficient of the variable n. But if it's going up by a multiplying factor, you might use that as the base of an exponential. And this last one here, again, if I looked at the differences, it'd be 3, 5, 7, 9. Okay, so again, it's not the common differences that we were getting in these first two problems, but you can certainly see a pattern there. Sometimes if you see a pattern and it doesn't establish itself as being constant until you go down 2 levels, so the difference between 3 and 5 was 2, 5 and 7 was 2. If you go down 2 levels, that might be a hint that there is a n squared involved somehow. Again, down 1 level, you use linear, n to the first power. Down 2 levels, you use a quadratic, you use n squared. Now, 1 squared is not 4, 2 squared is not 7, 3 squared is not 12, but if you kind of heard me as I was saying that, each one of them was missing by 3. So if I try to put on a plus 3 here, 1 squared plus 3 is 4, 2 squared plus 3 is 7, and so on. 3 squared plus 3 is 12, and it looks like that's working. Again, this is not an exact science. We will certainly work on it through sections 8.2 and 8.3 on how to formalize some of this, and maybe there will be particular ways to do certain problems, but in the end, you're going to have to do a lot of work of this on your own, just trying to figure out the pattern and trying to represent the pattern. Okay, so we'll come back in our next video with some more from section 8.1. It's going to take us a few videos to get through section 8.1, but hopefully that's a good introduction to you for sequences.